for part 2 of question 7. Apologies, but a class came into the room where I was making that video. So I've been trying to find a room. Hopefully this one will be alright. Show that the lion's speed decreases over time, whereas the zebra's speed increases over time. So I discussed that in the last video. The zebra's speed increases over time. Again, I think drawing the graph really shows what's happening, and that would be enough rather than going to a second derivative or anything like that. So you would be writing a statement. I don't have a pen. Right, so I did line in the last video. For the zebra, you could say, well, I just want to consider times greater than 0. So this is for my zebra at t equals 0. The velocity is 0. As t approaches infinity, the velocity approaches 20 from below. And then just say refer to graph. I suppose we could also show that for values greater than 0, the velocity will never, the velocity can never be 0 and can never be negative. So we could inspect these functions and say we're never going to get a negative velocity from the function. For example, the lion. Your function looks like this. You could say for all t greater than 0, v of t is always greater than 0 as well, right? Just to show that those velocities will always be positive. But I think the graph really explains everything we need. Once you've drawn an accurate graph, you can refer your reader to that. And the graph should help with the rest of the question too. So let's actually look at the rest of the question. It says, find the integral from 0 to 3 of the v1 function. Now v1 was the lion, okay. And interpret your answer. So I don't think I'll do that. Or maybe I should. To show that the numerical answer is not that important to me. If we're doing the integral of our lion's velocity, the interpretation is that that's the distance and also the displacement. It's this one, isn't it? V1. That the lion covers in 3 seconds. I don't know where that point is. I'm not exactly sure where 3 is along here without technology at the minute or without doing some further work. But an interpretation is that it's the distance the lion has covered from his starting point, or when they started the clock. Now, to do this integral for this function, we'll just run through the antiderivative, given that it's an exponential function. So what I'd be doing is keep your 15. Right. E is its own integral, so rewrite this. Then imagine you're doing a derivative. If I was doing a derivative at this point, I would be multiplying by minus 0.1. But I'm not, I'm integrating. So I'm going to divide by minus 0.1, like this. So 0.1, right? That 0.1, it's like a tenth. Yeah, it's like I am dividing by a tenth, which is equivalent to timesing by 10. Right? So our antiderivative equation will be minus, there's a minus there, 150 e, this is our antiderivative, and we'd have to evaluate that between 0 and 3. As in, go to the calculator, minus 150 e, what's 3 times 0.1? It would be 0.3, so it's minus 0.3 minus 150 e to the 0, which will just be minus 150 when you plug that 0 in where that t is, right? So this will end up being plus 150. This bit here, this is going to be a number, what's it going to be, a negative number. Will it be smaller? I'm not sure what e to the 0.3 is. So we'll just go to the calculator with it. Okay. Now the next part, they didn't just have what's the integral of one of the functions, they had v1 minus v2, interpret your answer. So let me make some room. v1 minus v2. So the integral of v1 minus v2, that's like, if I was to separate these out for a minute, just for the sake of clarity, treat them separately. I've got the distance of the lion, distance the lion's covered, subtract away the distance the zebra's covered. So the lion's got a head start here. His area under the curve, representing the distance, will initially be bigger. He's going to be covering a fair bit of distance. The zebra's not covering, if you think about rectangles or areas under the curve, the zebra's not covering much at the start, but by the time he gets out here, he is. So we have the lion's distance minus the zebra's distance. Is it the same as the distance between the two animals? Well, yes and no, just remembering that they started 40 meters apart. So I'd probably just leave that as it's the distance the lion's covered minus the distance that the zebra's covered. Now, if this ever got greater than 40, there'd be a problem. Right? So if the lion ever, because they started 40 meters apart. So if the lion ever covers more than 40 meters distance than what the zebra covers, it means that the lion caught the zebra. Right? To put this into a sentence, I would say the difference in distance, that the lion has travelled compared to the zebra. Right? Now, if it was a negative answer, it means the zebra is increasing his distance from the lion. If it's positive, it means the lion's getting closer to the zebra. If it's ever greater than 40, it means the lion caught the zebra. So hopefully that's clear. And I think that's where this question's going, is did the lion catch the zebra? But there's something else I'm interested in, is where are their velocities equal? Let's refer to the question though. Explain why the lion will be closest to the zebra when the velocities are equal. Oh, that's interesting. So at this point of intersection, that's where the distances, let me start again. We've got a point of intersection here, right? Intersection. It's where the velocities are the same. The textbooks just told you that this is the closest in terms of distances that the animals could ever get, right? And why is that? It's because after this point, the lion's velocity decreases. So I would say, and therefore, and the zebra's velocity, let's write something like after point of intersection, of velocity curves, V1 and V2, right. The zebra's velocity keeps increasing. And that was V2, isn't it? V2 increases, whereas the lion's decreases. Velocity. Now, if this was in a test, by the way, I'd be writing proper words here. It's just my pen's a bit dodgy, right? Decreases. Therefore, the lion can never get closer to the zebra from this point onwards. So it's really about examining that point of intersection of velocities. You could say before they reach the intersection, if we looked from the other side, the zebra's speed's increasing, but he started at 0. The lion's speed's decreasing. I think this is the way to go, actually. So after the point of intersection, where the speeds are equal, the zebra's velocity would be increasing, lion's velocity is decreasing, therefore they can't get closer at that point. Okay? So the book's question's slightly different. They're saying, why is it that is the closest point, right? Because prior to that, the lion was always faster than the zebra. Okay, we could say, probably want to write that as well. Therefore, zebra, I'll just finish this thought. Zebra covers more distance. We could say prior or before, prior to point of intersection. Right. Lion's velocity, which was V1, is greater than zebra's velocity, which means that the lion is gaining on the zebra. So here you can see the lion's going faster than the zebra, so it's closing the gap, right? It's getting closer and closer and closer until the velocities are equal. Then the zebra is going faster than the lion, and so the distance between them would increase. Okay. You would need to write a coherent answer using the English language. Right? That's a write a sentence question. Now, find the time at which V1 equals V2. Using technology, this will be fairly straightforward. You find the point of intersection. Maybe I can do that quickly, although I'm conscious of how long these videos can go. If I can remember the equations, so let's clear that. You just type them in, right? So we had 15. Let's clear that actually. 15 e power of minus 0.1x. Then we've got 20. Oh, 20 is already there. Minus, now I think it was 20 e minus 0.1x. I'm graphing that. Let's think about the window. I don't need negative x values. I'm probably going to need some positive x values. Scale, let's just set it to 1. Y minimum, well, it can never go beyond 20. So we'll try that. What happens? Yeah, that's okay. All right. So we could find this point of intersection. Second calc, intersect. First curve, second curve, guess. There's only one point. And it's at 5.60 seconds. Okay. Now, if you needed to show working, we're working out an x where the y values are equal. So we need to find out. Oh, lost my pen. Back. Where does V1 equal V2, right? So we could say 15e to the minus 0.1 t equals 20 minus 20e minus 0.1 t. Let's put all our t's on one side. Let's put them on that side. Yeah. Do this. Minus 20 equals 5. What am I doing? It's got to be minus 5. Minus 5 e to the minus 0.1 t. Because you've got the same power here, see this, right, and this are the same term. So it's like I've got 15 of them here and I've got 20 of them here. So, hang on, it's minus 35. What am I doing? Making mistakes, that's what I'm doing. That should be a minus 35. I'm not sure if I can fix it. Oh, there we go. Minus. That looks really dodgy. I'm going to write this again. I want that. Okay. So yeah, it's just like saying a 15x, and over here I've got a minus 20x. Let's make them positive from the get-go. 35e to the minus 0.1 t equals 20. All right, so e minus 0.1 t is 20. Divide 35. Well, those numbers both divide by 5. So 4 on 7. Now I need logs. Taking the log of both sides. Log 4/7. That'll be a negative number. We're getting minus 0.1 t equals this log that I've already written. And we've got, therefore, t is the log divided by minus 0.1. This is a log of a number smaller than 1, so this will be negative, and that's negative as well. So you will get a positive answer. You go to your calculator, type it in, and you should be getting 5.6. Calculator, clear, no, it's not going to work. I need my pointer back. What do we, hang on. And if I type it in here, will you see it? So it was log 4 divided 7. Might have to clear the screen, but you might be able to, divide minus 0.1. We should be getting 5.6. Yeah, you can kind of, that's good enough, isn't it? 5 point. Now, for 3 significant figures with the rounding, just a small little side note. If you're being asked to write this as 3 significant figures, then write it as 3 significant figures, so you can include that 0. Right? That's your 3 sig figs. Right? Okay, so what we could do is actually compute that integral. If the distance is smaller than 40, sorry, larger than 40, it means the lion caught the zebra. We could do it on the graph quickly, but we could also do it the long way. So back to graph. No, we can't really. We'd have to do the blue, then we'd have to do the red. We'd have to subtract them and see what the answer was. All right, let's just do it by hand from the get-go, because distance between, well, the difference in distances covered is V1 minus V2. So we need to do this integral as directed by the book earlier. We now need to go up to this point. I think 5.6 is good enough, right? And see, it's like if greater than 40, it means lion caught zebra, because remember they started 40 meters apart. So I've already shown you an integral using E. Right, I'll just do a little bit more working out, but really you're going to the calculator I think here. So your V1, that's lion, minus your V2. Note the use of brackets. And then that's so that when I actually calculate this integral, I'm going to have 15 of these e's minus 20. I'm going to have 35 of them. Right? Minus minus becoming plus. Or minus and negative, I should say. Same as. Right. And we could work out what that answer is. Clear a bit of space. No, wrong button. Undo. Control Z. Okay. I think you'll be able to see the screen like this. Let's try. So we want integral from 0 up to 5.6, where we, from the graph, determined that that would be the minimum possible distance between them. And so we've got 35e to the power of minus 0.1x minus 20. Right. If they're asking for full working out, I'm going to have to do the antiderivative of this. Right. but I've already shown you an antiderivative where E was involved, so I think I'll skip doing it the long way. All right, they got to 38 meters difference in their distances covered, but they started 40 meters difference, right? The lion was 40 meters away. The lion's going faster than the zebra at the start. You need to see this background, right? So it's covering more distance because its speed's higher. The zebra's starting from standstill. It's not covering as much distance, right? So all the way up to the point of intersection, the lion's catching the zebra. We've gone out to that point and we've figured out that the difference in distances covered was 38 meters. So the lion therefore got to within about 2 meters of the zebra. Right? So lion, just to finish off, it was approx 38 meters. Right. Lion does not catch zebra, right? Because it needed to cover 40 meters. It didn't. And then from that point onwards, the zebra is now running faster than the lion can run. Therefore, it's going to cover more distance and the lion can no longer catch it. I'll just look at the question. Have we answered everything? Did the lion catch the zebra? No. How close? Well, about 2 meters. I can't remember exactly. You can do it a bit more exactly. Yeah, 1.9, 2 meters. That'd be close enough. All right, so that's a really interesting question. Hope you enjoyed that. Stop.